So let's go ahead and get started. Let's sort of recap where we are and where we're headed with this concept of mechanics of deformable bodies. So really what we've been focused on over the past couple days is trying to look at these, mechanics-based problems in a different light. And so far, what we've really tried to do is take the geometry out of the equation, okay? And what do I mean by that? Well, just for the purposes of discussion, let's say I'm looking at, something like this eraser. An easy way of calculating, let's say, the volume of this eraser would be the area times the length. Is that a fair point? Area times the length, assuming I can, stay a hold of it. All right? We've taken the area out of the equation by defining this concept called stress. Well, we don't care so much about the load, we care about the load per unit area, and that's where this whole stress concept comes into play, right? So we take the area out of the equation. We've taken the length out of the equation with this concept called strain, okay? We don't care about the deformation, it's the deformation per unit length, okay? That make sense? Everybody okay with that? All right. That only gets us so far, okay? It does help us address some of the issues that we had earlier. For instance, that very first example I showed you all with the paper clip. I myself am strong enough to take this paper clip and permanently deform it, but I couldn't do that to that large metallic bar because, like we said, it wasn't the load that mattered, it was the stress and what have you. That still doesn't characterize aluminum. That still doesn't characterize copper. That still doesn't characterize concrete. Once you take the geometry out of the situation, so you start looking at things in terms of stress and strain, we can then go through and start to characterize the way these materials behave. And that's where the concept of a stress-strain relationship comes into play. You might hear them called constitutive relationships. And all that basically means is taking the geometry out of the equation. How does aluminum behave? How does copper behave? How does steel behave? How does concrete behave? How do polymers behave? How does fiber-reinforced plastics behave? And what have you. Each material has its own unique set of stress-strain relationships, and it's one of, if not the most fundamental piece of information that we need as engineers in order to be able to use that material for design. If I'm designing some beam, once I know that that beam is made out of steel, I can then determine, well, how deep does that beam need to be? How heavy does that beam need to be in order to safely resist those forces? All right. Make sense? So my big thing is I want to make sure that whatever you're learning, you got a good understanding as to why you're learning it. So I usually try and spend a little bit of time looking at that. All right. So one of the best ways of characterizing a material's properties or a material's behavior is to literally take a chunk of that material and break it, okay? Now, I say that like it's a bunch of cavemen just, taking it and breaking it. Now, this is a highly controlled laboratory experiment, but in the end, that's essentially what we're doing. We're taking material and at a constant controlled pace, increasing that load, at a controlled pace, and recording that material's response, okay? Now, we do that usually very commonly through either a tension test or a compression test. Take a member and yank on it in tension, or take a member and push on it in compression, okay? It's one of the most common examples. How many folks have already had 215? Did you do this in there? Okay, all right. If you're in 215, you will do this. If you're a civil and you take CE 321, you will do this later, okay? So everybody in this room at some point or another will go through the process of doing a tensile test. For the purposes of this class, I'm just going to show you one just so that we can at least be able to speak the same language. Okay. So, these are examples of some different types of samples that you would test. These ones up here are typical things like your A505 specimens. These ones down here are dog bones. Notice how the geometry is fairly similar, at least for these tensile specimens. You have a wider section up top than you do down below. The idea is that your testing machine will either grip these threads on these upper specimens or grip this notch for the lower ones. And because the specimen is thinner in the middle, we know that when we test it, failure is most likely to occur in the center right here. Make sense? That's for a specimen in tension. Materials like concrete or cementitious materials like that, they tend to behave better in compression than we do in tension. The whole point behind the philosophy of reinforced concrete is that concrete is a material that behaves very poorly in tension, so we place reinforcement, like rebar, we place that rebar where the element is experiencing tension. That's the whole point of putting rebar in concrete, is to try and increase its resistance to tension. That's the whole reason why we do that. Okay? So when we test elements, we test concrete elements, we usually cast a concrete cylinder. They can either be 6 inches in diameter by 12 inches tall, or 4 inches in diameter by 8 inches tall. Just depends on what standard you're going off of. And take it, apply controlled force, and crush it and record its response. All right. Sound good? All right. So what I want to do is look at a stress strain curve test. I have a link to it here, but I also have a hard copy of the video that I'm going to show you all. You can find it right there. It's on YouTube. But what we're going to do is I'm going to probably shut up at least as best I can and let this person explain these two stress strain tests, and we'll go through, and once we've explained, or once we've watched the video, go through and sort of tackle each one of those topics one at a time. So let me go ahead and pull this up. All right. So I have this. Let me go back to the very beginning. All right. I'm going to go ahead and press play. If I need to raise the volume, just a minute.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared.
That's a device that will measure how much it's
Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 mm. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there.
Suspense kills you.
In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM.
Again, force over area.
In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece.
Gotta be careful when you're doing that. That can be sharp. So.
On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material.
Notice how that load is going at a constant rate.
But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength RP 0.2 is equal to FP 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture and percentage reduction of area are calculated in the same way as in the first test.
Now, like I said, don't take any of that notation to the bank. I mean, we're going to, like, we don't use S for area, we use A for area. But in the end, a lot of what they're talking about is fairly similar. So let me go here. So you noticed that what happened in that video was they did tensile tests of two different materials. The first one was sort of a steel type material, and the second one was aluminum. Now, these graphs may look a little different, but by and large, it was essentially the same type of patterns that you got with both tests. Now, what we're going to do is we're going to investigate the low carbon steel one a little bit in more significant detail, just to identify some of the common points and make sure that everybody understands what's going on. But the nice thing about stress strain tests is that, you know, A, you can take the geometry out of the situation, and B, you can really start to classify the way these materials behave. You know, for instance, while this may not make a whole lot of sense right now, just from a graphical standpoint, you know, we get different stress strain responses for aluminum than we do for steel. So the design decisions and the limits that we use for aluminum versus steel would be different. Okay, they're obviously different materials. They're going to have different properties, different behaviors. This is a way that we can use to determine, well, what are those values that we can use for the purposes of design? Okay, does that make sense? All right, so we're going to take a typical tension test for structural steel, and I've got it sort of broken down into various, you know, I guess various points of importance. And we're going to take each one of these points one at a time and try and explain what happens. You know, as we take this piece of material and yank on it, what happens from beginning to end, okay? So let's start off with the very first region, okay? Now, what I've done here on these slides, you'll notice I've got OA, because I'm going from point O to point A, and then AB, BC. You got to get what's going on, right? Sound good? All right, let's start off with the linear region, okay, this OA. This is when you've got the bar or the tensile specimen, whatever you want to call it, and you're applying load, but there isn't much load on it at all. Very small amount of load, okay? I say very small, but in most cases it can also be very large as well. The long and short of it is, though, is in this first range, you're applying load, and really the specimen is acting like a rubber band, okay? So if I have a rubber band, what happens? I take that rubber band and I stretch it. I let go, what happens? Snaps back, and it snaps back to exactly the same way it was, right? Assuming I didn't stretch it like that and snap the rubber band, right? This is what we call elastic behavior. In other words, when I apply a load and then release it, it goes back to the way it was, okay? Stress and strain are proportional to one another. And if you go back to math, if you have y and x and they're proportional to one another, they're usually proportional through some term that we call a slope. You know, y equals mx. You know, that m is a constant of proportionality that relates how much x changes. That will in turn, based on this slope, tell us how much y changes, right? That's what a slope is, okay? Materials have a slope constant that we tend to call Young's modulus, or the modulus of elasticity. If you've had Engineering 215, I've got to believe you've heard of this term. Am I correct? Y'all that are in Engineering 215, are you, have you talked about it yet? You will, probably very soon, okay? The idea is that this applied stress and this resulting strain in this linear range are proportional to one another, okay? And they are proportional to one another through this constant E, okay? Now, E is a material characteristic, okay? In other words, there are different quantities, there are different values of E for steel than there are for aluminum, than there are for concrete, what have you. For instance, if you take me for a structural steel design class later on, one of the numbers that will burn into your memory is that the E value for structural steel is 29,000 KSI. Okay, it's 29,000 kips per square inch. It's a constant property that is associated with structural steel. Okay, go to Appendix I in the textbook, and there's E values for all sorts of materials: aluminum, brass, copper, you name it. Okay, sound good? Okay, now a material will only behave linearly so long. Okay, and what will happen is, once you reach a certain point, which is what we call the proportional limit, when it stops being proportional, you will experience a phenomenon known as yielding. Okay? Now, you have seen yielding before. I showed it on day one when we had the paper clip. I took the paper clip and I applied a load, and I reached this magic point where that paper clip started to deform. I let it go. Those deformations were stuck. Okay? Yielding is the process of those permanent deformations. Okay? But what exactly is yielding? I mean, yeah, that's an example of it, but what is it? I do not want to get into material science very heavy with you all and start talking about the chemistry of the situation, the crystalline bonds in the metal and whatnot. I don't want to get into that. But to explain it simply and quickly, okay, what I want you to think of is, imagine you've got this piece of metal, in this case it's steel, and I want you to zoom way far in and start looking at the chemical bonds between those molecules. So you've got this component of steel and this component of steel, and they're bonded. Okay. Now metals tend to form this crystalline structure. It's a lot like just these cubes. You see a element, just like a big cube type structure. Those molecules, those components of steel, are held together by these chemical bonds, these electrical bonds. Well, you start applying load and you start yanking on this thing. After a while, you start stressing those bonds to the point that they start to break. Okay, the bonds start to break inside the crystalline structure of the metal, and it starts to deform a little more. Okay, now there is a point when it stops becoming linear and it starts getting into this phenomenon where the bonds have broken, and we call that the onset of yielding. It goes past the proportional limit. That proportional limit is just when it stops becoming linear. So we're talking about when those bonds are starting to break and we start to hit that yield stress. Does that make sense? Everybody okay with that? I don't want to get too heavy into the material science. That's not really why we're here. I just want you to kind of get a little bit of an understanding as to what it is we're talking about. Sound good? Okay. So those bonds have broken. Okay, so imagine you've got this structure of molecules and alloys held together by all these bonds, and the bonds have broken. What happens then is the bonds have broken, the specimen's like, whoa, wait, we got to sort of rearrange and shimmy around in order to be able to resist this load. So what's happening is you're applying this load. There's this sort of plateau region where what's happening is the structure inside that metal is trying to reorganize and rearrange itself in order to figure out, well, if you're going to start applying more load, I got to rearrange myself so that I can safely resist it. Excuse me. So we call this the yielding region, and what's happening is this whole rearrangement of the internal structure of the steel. What's happening is by rearranging itself, it's freely deforming. You're not increasing the load, and it's still having to freely deform and to sort of figure out what's going on. Figure out a way to resist this load. Now, once we release, let me go over here. Now, once this specimen has started to rearrange and figure out what's going on, it can then accept a little more load in its rearranged state. We call that the strain hardening region. Now, it's accepting load. It's not accepting it at that same stiffness. When I say stiffness, I'm talking about the slope of that line. This is a really large slope. This is kind of a small slope. Okay? So after it's realigned, it can accept load, but not to the same degree it could before. All right. Sound good? Okay. All right. Now, one of the interesting things about yielding and about material behavior is what happens when we unload the specimen, okay? Now, we talked about the rubber band concept before, okay? I take a rubber band, I apply load, I let it go, it snaps back to the same location. Once you've crossed that yielding point where you're breaking those internal material bonds inside the steel, there's no going back, okay? You have locked in those permanent deformations. Think of the paper clip. I crossed that point, that paper clip was bent, it was staying bent, okay? All right? The interesting thing is, if I take that load off, it stays bent. But if I go back and reapply load, it goes back to behaving in an elastic fashion, and it'll accept load at that same slope. It's an interesting property of material science, and you all will see this later physically in either Engineering 215 or CE 321. Sound good? Okay. Now, one of the things the video was talking about is this concept of yielding. You know, yielding is going to become a very useful limit in terms of design. For instance, I'm designing this shaft for a transmission for a car or what have you. I'm designing it out of steel. I want to make sure that everything behaves the way I would like it to, so why don't I say the stresses shouldn't exceed the yield stress, okay? Because everything below the yield stress would be linear, okay? In other words, I apply a load, I let it go, it goes back to the way it was, which is really great in terms of design, okay? I don't want to design some component that, if avoidable, is going to be yielding over and over again. Because, I mean, how many of you all have worked on a car before, okay? Worked on a car, it would bug the hell out of you every time you change the oil or change the brakes or something if the parts were in different places because it all yielded. That, you've got to limit those stresses in some fashion so that, it's able to be designed, able to be put together, and that it performs the way you want. So a very useful limit is the yield stress, or maybe the yield stress with some factor of safety, and we'll talk about that later. But what about aluminum? Aluminum didn't have this nice, pretty plateau of yield stress. Aluminum behaves a little differently. We got to have some value, some number to use, okay? So sometimes we use a number called the offset stress. The idea is, okay, we can pretty well determine this slope, this elastic region, take that, offset it at a 0.2% strain. Remember, 0.2% would be 0.002. That's the number, right, in terms of the percent. Offset that out and figure out where this line intersects and say that's our yield stress for purposes of design. Because something like aluminum, it doesn't have a nice, pretty plateau that we can go up on. We got to use something, right? And a 0.2% offset stress is a pretty useful value in terms of design. Does that make sense? Sound good? All right. All right. So like I said, once that structure inside the metal has started to realign, it says, okay, I'm okay. I've sort of shifted myself around to where I can accept that load. Let's keep it coming. Let's start applying more load. It'll accept load, but it will certainly not accept load at the same strength that it could earlier, okay? So this is what we call the strain hardening region. Now, similarly, we reach a point when, okay, we're starting to get to the point where we're done, okay? And that's what we call this ultimate stress. Sometimes we'll call it the tensile stress, sigma sub u, sigma sub tensile. In structural steel design, we call it F sub u for the ultimate stress. So let's say for a typical structural steel that we use in buildings, a yield stress of 50 KSI is very common. An ultimate tensile stress of 65 KSI is pretty common. All right. Sound good? Once that happens, we're starting to get to the point where we're losing capacity and this thing's going to go, and that's where this necking region starts to happen, okay? So you all saw that in the video, at least with that steel section, the point in the middle started to narrow up. So what I want you to think of is in terms of stress. What is happening to the area at that necking region? What's happening to the area? Like if I cut a section and look at that area, it's getting smaller, but the load is going up, okay? I'll probably mention this later, but I wanted to mention that now. That's sort of the reason that these two curves are trailing off, how you've got a different curve up here than you do down there. There is a difference between what we call the engineering stress-strain curve and the true stress-strain curve. For engineers' sakes, when we determine this stress, remember how we said load divided by area? We take the load and divide it by the area at the very beginning of the test. But what we have to recognize is that throughout the test, the area is changing. So there's a difference between an engineering stress-strain curve and a true stress-strain curve. That's just sort of a material science characteristic that I wanted y'all to be aware of. All right, sound good? The big thing is that for a given material, if we subtract out that geometry, we should get the same stress-strain relationship for steel, regardless whatever size the specimen was at the beginning. So it definitely helps us out in terms of design. In other words, if I had two different steel bars, assuming they were the same material, but they were different lengths, different areas, and we did the same test, we get the same result. Okay? All right. Sound good? All right. Okay, and this is what I was talking about earlier, the concept of engineering stress strain versus true stress strain. I got a little bit ahead of myself. You aren't going to have to worry about true stress strain. It's just something I wanted you to be made aware of, just from a theoretical concept so that you understood what was going on. All right. Sound good? Okay. Now, what I'm going to do is we're going to do an example. And the example is going to be looking at a stress-strain curve. And essentially, what we're going to try and do is take this curve and characterize a number of things. We're going to try and plot the stress-strain curve. We're going to try and look at the theoretical modulus of elasticity and looking at this 0.2% offset. Now, plotting this curve, I don't know about you all, I do remember math, but looking at an equation like that, I'm like, God, how do we plot that? I don't remember what that looks like. I'm not that good. So what I'm going to do is I'm going to use trusty old Microsoft Excel. I assume you all should have a fair amount of experience in that with Engineering 111. Am I right? Been a while maybe, but we're going to break out some Excel and see what we can do with this. So we're going to plot this curve, see what it looks like, and we'll see if we can determine a theoretical modulus of elasticity and look at the 0.2% offset. So let's open up Excel. I'm going to recommend Windows 10 to the people in this class, so I guess pretty likely. Again, I got jokes, so. I told some of you all, but I didn't tell everybody. I had a couple of students come up to me and said they were getting fired up for Circuits Lab. I said they were getting wired up for Circuits Lab. All right, okay, let me turn my mouse pointer on. So what we're going to do is plot this curve out, and let's see, I'm not 100% on terms of how far we should plot it out, but we'll just sort of guesstimate it. Okay, now let's sort of type some stuff out, make sure you all can read it. Strain, stress, KSI. Y'all read that? Okay, all right. So this is XY data, okay? So we'll take some strain values and then calculate some stress values and plot it out. So 0, all right. I'm going to keep these strain values pretty small, okay? So we'll do something like, I don't know, 0 or equals this plus 0.0001. Like, we'll keep them pretty small, okay? So if I go through, and let's see if y'all remember this from Excel, if I grab, see how my cursor, see how I hover over here and I get that sort of black hatch symbol, plus symbol right there, I can drag that down and it automatically fills those in. Let's drag that down a little bit. Let's go to, I don't know, we'll go down to about right here. That's probably good enough for government work. Actually, wait. What does the example say? Does the example have a limit? Let's see. It says, there we go. Valid from 0 to 0.03. Let's just use that. So let's drag this down to 0.03. So I got a little bit further to go. Let's see. Just a little bit. Something about like that, right? All right. So let's see. Let's copy this over so I have it, for reference. Okay. So that's my equation, right? So let's see what we can do. So equals 17,500 times that, right? Divided by the quantity 1 plus 240 times that, right? And then all I got to do is take this and just double click that, and now I got that data, right? Sound good? All right. Let's bring this, let's show that so we can actually see what's going on. Okay. So now we've got our stress strain data laid out. This is our strain. What are the units for strain? Anybody remember what the units for strain are? It's a trick question. There are no units. There you go. Because it's change in length over original length, so it's inches per inch or millimeters per millimeter. There are no units for strain. Okay? So strain's unitless, and we're saying the stress is in KSI. Am I right? This was for KSI? Yeah. For the purpose of what we're doing, it doesn't terribly matter, just as long as you're labeling it. Okay. So we need to plot this out. Now, just so you're aware in terms of our convention, we typically plot our load or stress on the y-axis, and we plot our strain on the x-axis, okay? Just so everybody's aware, so make sure you don't get that backwards. So I'm going to go through, I'm going to say insert. We'll say insert a plot. We're going to do a scatter plot, okay? And since I got a lot of points, I'm just going to use this one, the one with the straight lines, because it's not going to matter. So let's select our data. We'll add a curve. The x values are the strains, so all the way down here. Our y values, we'll just drag from the down, we'll say. About like that. Okay. And there's our data, right? That's our stress strain curve. So keep in mind when you're doing this, for real, you need to add axis titles. So down here we'll say strain. Over here we'll say stress, and we'll put KSI, so that we're all aware of what's going on there. We'll then say, this is for copper alloy, so I'll say, stress, strain, curve, copper alloy. So now I've labeled that out. Okay. Sound good? Now, a couple problems with this data. We don't have that nice, pretty yield section, that set of yielding, or that yielding plateau that we would like to say, there's our limit. It doesn't exist. So this is a problem where that 0.2% offset would be very, very nice. Okay? Now, there's also another problem, though. Okay? Another problem with this is E. Remember, let's go back. What is E? E is that Young's modulus, that modulus of elasticity. It relates that elastic behavior, how much strain is proportional to this much stress, and what have you. Now, we said that E was a slope, right? It was the slope of that linear region. But we don't have a linear region. We have a very highly nonlinear region. So let's bring it back to day one as freshman or sophomore, whenever you took it. How would I get the slope right here? The derivative. Okay? So I need to take the derivative of this function and figure out what the value of that derivative is right here. Bringing it back. Everybody remember this? Okay. All right. Okay. So, oh goodness, getting all tangled up. All right, so example 4. All right, so we had 3 tasks. Number 1 was plot the curve, which we can just see Excel or the video. All right? And the second step is this E value. All right? Okay. Now let's be clear. All right? My stress function is 17,500 times E, or epsilon, I keep saying E, epsilon, 1 plus 240 times epsilon. Now, if you don't like dealing with the sigmas and epsilons and it's a little confusing and it's not as familiar, you could think of that like this. Y equals 17,500 times x over 1 plus 240 times x. It's the same thing. Remember, strain went on the horizontal axis, stress went on the vertical axis. So this is sort of our y-axis, and this is sort of our x-axis. So if you want to think of it like this, that's more than welcome to. You're more welcome to. That's fine. All right. So how do I determine the slope of a curve? Just going back to Calc 1, what do I do? Take the derivative. Remember, what is a derivative? It is a rate of change. It is how much y changes as a function of how much x changes. That is a slope, okay? So if I want to determine, E at any given point, I need to take the derivative of that stress function, right? Just the derivative, right? Now I know it's 8:30 in the morning. You're thinking, oh no, not calculus. I know, but it just makes sense. Everybody okay with this? Isn't too bad, is it? All right. So we're going to bring it back for you calculus folks. So we're taking the derivative with respect to epsilon of 17,500 times epsilon over 1 plus 240 times epsilon. Or if you want, you can say the derivative with respect to x of 17,500 times x over 1 plus 240 times x. Everybody okay with that? All right. So let's do a couple things. First off, what can I do with that 17,500? Take it out front, right? It's a constant. Remember, derivative rules. If I have a constant times something and I'm taking the derivative of it, the constant can go out, right? So constant can go out, 17,500 times something. I have the derivative of a fraction, right? So if I got the derivative of a fraction, that means I got to use that whole quotient rule. Remember that? The bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Y'all remember that? So what we got? The bottom times the derivative of the top, which in this case is just epsilon because I took the 17,500 out, okay, minus the top, which is just epsilon, times the derivative of the bottom all over that squared. Sound good? I know it's bringing back all that calculus stuff. No, I mean, calm down. I can tell you're all really excited. So. There we go. I'm going to get some laughs, I promise. All right? All right. Let's do a little bit with this. Okay. So what's this first derivative? What's the derivative of epsilon? 1. So all I've got up here is 1 plus 240 times epsilon. Minus. Okay? Now, think. We got epsilon times the derivative of this. What's the derivative of what's going on inside this parenthesis? Is going to be right here. What's the derivative of 1? 0. What's the derivative of this? 240. So it's going to be minus 240 times epsilon. All over, whoop. So, therefore, what's going on up top? The 240 epsilons are going to cancel. And if I wanted to simplify this, would a fair way of doing it be this? That fair? Not too shabby, right? Okay. All right. So far, so good. Now, let's have a little bit of an exercise with this expression just to make sure we understand what's going on. Okay. What is this? This is the slope of that line at any point. That's what that is. It's the slope at any point. All right. Now, let's bring it back. I'm going to go back to this Excel sheet. All right. Let's say for the purposes of the discussion that this curve went like that. How would I determine that maximum? Find where the slope equals 0. Okay? So that function could be useful if we wanted to find the maximum allowable stress on that given material. So far, so good? Okay. But what we're trying to find is a theoretical value of E that we can use in our calculation. And E is that initial slope. So we've got a function for E. If we want the slope right here, what do we have to plug in? Epsilon equals, well, that would be the offset. I'm talking right here. 0, yeah, because we'll see if let's hope my pen works. What I'm trying to do, I'm trying to find the slope right there. Okay, so this is the slope E at epsilon equals 0. This, what we're going to do later, that's going to be, epsilon equals 0.002. That's how we're going to find that offset. We've got to find E first, and then once we have E, plug in this strain and figure out where these intersect. Sound good? Okay, all right. Oh. All right. Does everybody have this? You want me to hold it up here for a little bit? That's fine, that's fine. Everybody good? Okay. All right. So I'm going to go on to the next one. So, for a theoretical E, we can say if E is 17,500 over 1 plus 240 epsilon squared, therefore what we can use for our calculations is E at 0. So, what am I going to get if I plug this in? Well, on the bottom, I will get 1 plus 0. All that squared is 1. Anything divided by 1 is itself. So that's going to be 17,500. And I've been pretty fast and loose with the units on the top, but that's going to be 17,500, and that's going to be KSI. Okay? Because the stress is in KSI, E times the strain is unitless, so E and stress should have the same units. All right? And that's going to be my E value for when I do calculations later on. All right? Sound good? I need something to go off of. That's a reasonable value. Any questions? Not too shabby, right? Okay. All right. Now we got to look at this 0.2% offset. Okay. Now I'm going to take it back even a step further. Okay. Let's go back to when you all were in high school or whatever, and you had two curves that intersected, and you wanted to figure out where they intersect. What do? You have, let's say, two lines, you know, this line here, this line here. How do you find out where they intersect? You set the two equations equal to one another and you solve, right? Y'all remember that? So what we've got is this. We've got, here's our data. This is our stress. This is our strain. What do we have? We have a stress-strain curve, which looks something about like that. What's the equation for that curve? It's sigma equals 17,500 times epsilon over 1 plus 240 epsilon. Let's be clear. It's not this. This was the derivative. This is the actual stress-strain curve, right? Now, I want to find that 0.2% offset. How do I find that 0.2% offset? I need to find this. And ultimately what I'm after is where those two lines intersect. Sound good? Let's talk a little bit about that blue line. What do we know about that blue line? All right. What's the slope of that blue line? It's that, right? We draw that at that initial slope. What is that point right there? Comma, think x and y. There we go. So 0.002, comma 0. What I'm getting at is this. Y'all remember this? Remember that? What do we know about that blue line? We know its slope. Its slope is m, which in this case is this e value. Then we have x sub 1 and y sub 1, which is the coordinates of that point. Now we have an equation of this line, right? So let's start plugging in. Although what I'm going to do is, just so we're using the same notation, I'm going to say or sigma minus sigma 1 equals e epsilon minus epsilon sub 1, just so we're talking about the same thing. Sound good? All right. And then over here, what do I have? I have sigma minus sigma 1. What's that first sigma value? It's the y value, which is 0, right? Equals 17,500. And since everything's in KSI, I'm going to leave that off and say epsilon minus 0.002. All right, and help me out. What is that? $17,500 minus 0.002, or times 0.002. See, I'm making y'all say it again. 35? 35. And see, if you think about it graphically, that makes sense, because go back to graphing. That has a positive slope, right? Going up like that. What is this term? It's the y-intercept, which is going to be down here, negative. Make sense? All right. So now, you all right if I go on to the next slide? Okay. So now, so we have equation 1. And equation 2, which is right? If I got equation 1 and equation 2, what do? Set them equal to each other and solve? See what we get. So Y'all have seen that before, right? When I draw these three dots, that means therefore. Okay, I just want to make sure. I've had students come up and ask what that meant, so. All right. Now, I don't like dealing with fractions very much, so I'm going to take all this, multiply it over here. You all have calculators on you, so I'm going to rely on you all a little bit. So remember, you got to multiply the whole term by the whole term. So that means we got to do a little bit of foiling. Remember that? I think you're better now. All right. So first times first. All right. Outside times outside. I'm not that good. 17,500 times 240. Say it again. So right? Okay. Inside times inside minus 35, and last times last, which is 240 times 35. What is that? Negative 35, but that doesn't really matter for what we're, say 8,400? 8,400. Okay. So now, epsilon. All right. So now, to keep this simple, I can cancel that and cancel that, right? Just subtract it from both sides, and I would get 4,200,000 epsilon squared minus 8,400 epsilon minus 35 equals 0. Now, I got to believe y'all can solve that one, right? I mean, they're big numbers, but I hope. Y'all good with that one, right? All right. Your Casios should do this, right? You just plug them in and they kind of do it for you. All right. Now, let's see. Here's what I've got. I want you all to check. All right. So I've got, now, this is a quadratic, so how many answers am I going to get? 2, right? And I got epsilon is negative 0.00417 and positive 0.00406. Is that what you got? All right, everybody else good? Okay. So, again, a quadratic, you get 2 answers. What's up? You got something different?
I got one of them.
Is it rounding? That's this one.
The other one is negative 2.06.
Really? Oh, okay. I mean, ultimately it ain't going to matter, but I will trust you all. I'm allowed, I think, 7 mistakes throughout the semester, so that's one of them. Only 7, though, so I will hold you to it. What was it?
Negative 2.06.
Like that?
Yeah.
And that's what you got?
Yeah.
Okay, all right. That's fine. All right. Now, ultimately, though, it doesn't matter. Why? Do we use this answer? We don't use this one. This is the only one that we use. All right? So, all right, there we go. Is this our answer, though? No. Why? What are we calculating? We're calculating a 0.2% offset stress, right? Not a strain. Okay? We take this value and then plug it into one of these equations to get the strain. Does it matter which equation we plug it into? No, because this is where they intersect. It really doesn't matter. So for simplicity, which one you want to use, 1 or 2? 2. So I'll say plugging in. And what does that come out to be? $36.05? All right, we're going to test that out. 36.05 KSI. So, all right. So really around 36. And that's about as accurate as we're going to get with how I'm going to test this out, because we're just going to look at it. All right. Sound good? Okay, all right. Everybody got all this written down? Let's go back to our trusty little Excel sheet. Let's see what we can come up with. Now, I'm going to erase a bunch of this, and you'll see why here in a second. Okay. We're actually going to plot two lines. Let me close all that. Move this over here. We're going to plot another line. All right. So I'm going to put another stress strain curve here. Okay? All right. So I'm going to start off with a strain of 0.002. Then I'm going to start off with a stress of 0. You see what I'm doing? I'm going to plot my offset line. Okay? Now, let's come up with another strain value, and it really doesn't matter what this is, and you'll see that here in a second. I'm highlighting it yellow. Let's call it 0.006. It doesn't really matter. Okay? All right. Now, what was the equation for that offset line? It was 17,500 times this minus what, 35? Did I do that right? No. I'm talking about the offset line. I'm talking about this. This is the equation of that line, right? 17,500 times the 35, or times strain minus 35. So equals 17,500 times this minus 35, right? Okay. Actually, for the suspense sake, I'm going to start off small, 0.0021. We'll start off small and see what happens. Now, what I'm going to do, I'm going to go to Design, Select Data, and I'm going to add another curve. So make this the X values, make this the Y values. Okay. See it right there? So watch what happens when I increase this strain. Watch what happens. Say that. Where did it cross? Oh, maybe about 36 KSI. All right. Anybody got any questions? Okay, so this is just, I mean, again, this value doesn't matter because all I was trying to do is just find a point where it crossed and just observe it, see if it makes sense. Okay? All right? And like I said, we got around 36 KSI. Like the answer I got, like I was tracking decimals, I got like 35.97. Hey, come on, you know, close enough for government work. Okay? All right? Again, I'm as long as you're doing it right, if those types of decimals are affecting your engineering design, there's probably something more wrong with your design. All right. Any questions? All right. I do have a take-home prize for you. I have a gift, a homework assignment. This I've got it due next week. I really don't think it's a lot of work. I do have some Excel work on there as well. What I've done, and I'll walk through a little bit of the assignment with you. A lot of it's fairly similar to the stuff we've done in class. I just want to make sure that you're understanding what's going on. 1, 2, 3, 4, 5. There's that. I just want to make sure that this stuff makes sense. One point I would make out, I did give you a problem where I've given you some data and then you need to actually plot that data and make some interpretations in terms of its stress strain. Oh, you almost one? I'm sorry. I can't count. That's what it is. All right. So I've given you all some data where you actually need to take it and plot it and make some interpretations. Now, I'll preface this by saying the data is in force and deflection, so you have to turn it into stress and strain. You know, divide the force by the area, divide the deformation by the original length. You know, so that you're on the same page. Okay. I've got that. I'm going to post that online. It's going to be due next week. Now, I think, was this in your handout, this slide? Was that one in the handout? Okay. So that way you have a picture of just this stress strain curve so you have an idea of what it should look like. I do have a couple other things that I want to very briefly discuss. We have a little bit of time, and we might as well go ahead and go through this stuff now because it's not going to take very long. I want to introduce you to some other material-related aspects, some secondary stuff that we haven't quite talked about yet, but that is very important. So one of those is what's called the Poisson's effect. So the Poisson's effect, and this probably makes sense if you think about it. Go back to that concept of the rubber band. Take the rubber band and stretch it. It gets longer, but if you use your noggin and you think about it a little bit, it doesn't just get longer, it gets thinner, right? Make sense? Well, that's called the Poisson's effect, the idea that as you elongate something, it gets thinner, okay? Now, this is a material characteristic, okay, just like E, okay? You know, steel has a different E value than aluminum, than copper, than brass, and what have you. Well, the Poisson's ratio for materials is similar. This is something that you would test and measure, okay? For structural steel, a very common value is 0.3. For concrete, a very common value is 0.2, okay? Go to Appendix I, and I say V, it's actually the Greek letter nu, go to the Appendix I in your textbook, and there's all sorts of Poisson ratio values for different materials. All right. We will talk about this in greater detail later, but what we have been talking about so far is axial load and axial stress. Take a member and yank on it. It generates an axial stress and an axial strain. They are related, okay? Similarly, if I take a value and I shear it, I get a shearing stress and a shearing strain. They are related. We call that the shear modulus, G. Now, you can derive G pretty easily if you've got E and you've got Poisson's ratio by just plugging and chugging. Later on, we'll talk about how we would derive this, okay? Takes a little bit of time to get there, but for now, just believe me, we will derive it, I promise. The only other thing I wanted to mention is the idea of a factor of safety, okay? Now, just, in my world, in structural engineering, we really don't use factors of safety the way that you think we would. Now, what do I mean by a factor of safety? I like breaking things. My general philosophy is any day with controlled demolition is a good day. So let's say I took this table down to the lab, okay? I put it under a large capacity actuator, and I started applying force until this sucker wanted to snap in half, okay? Now, let's say it snaps in half at 800 pounds. What I might then do is say, you can only put 400 pounds on it, okay? I'm applying a factor of safety. I'm not letting it be used up to that maximum nominal capacity. I'm saying, let's cut that off a little bit, okay? Now, factors of safety are a function of a number of things. Are there going to be variables in material characteristics? I mean, this table failed at 800 pounds. Let's say I was in a really destructive mood and I took all the tables in this room down to the lab, okay? But I'm making a legitimate point. Let's say this table failed at 800 pounds. Are you telling me that this table is going to fail at exactly 800 pounds? No, come on. There's uncertainty. Are you telling me this has got the exact same material characteristics as this? It's wood. Wood is a very orthotropic and variable material. There's going to be uncertainties with the manufacturing process. You're telling me these holes are drilled in this table in the exact same spot as these? No, come on. No. There's a little bit of variability, okay? And because of that, that creates uncertainty, and uncertainty leads to the use of factors of safety. In structural engineering, we do things a little different. We have a different design philosophy that you use because it's appropriate for structural engineering. For something like geotech, where the materials are, the properties are so damn random that there's no way of capturing it, we just say factor of safety of 3, and we go with it. Because geotech is very complicated. I mean, when you take a course in geotechnical engineering, you'll learn very quickly that the soil properties over here can be fundamentally different than the soil properties over here. That's just the earth. I can't change that. So in order to incorporate that uncertainty, we just use a factor of safety. We just say, let's divide it by 3 and go with it. It's just something to think about. So there is a difference between what is actually the maximum available capacity in a given material and what we're allowed to use. Okay, does that make sense? Remember that truss example? And I said, well, what if sigma allowable was 12 KSI? And my man here in the back said, oh, I ain't feeling that too much. Well, that's because he was thinking about a factor of safety. Without even, codifying the idea, technically it was good, and that's pretty close, okay? Now, what is the factor of safety for you versus you versus you versus you? Well, that's a function of A, the design codes that you're using, and B, a little bit of engineering judgment, okay? That's why you get a stamp, so that you can use your judgment to appropriately design things. Any questions? Okay, so just a heads up on what's coming next. So what we're going to do next is we're going to sort of take this concept of stress and this concept of strain and start to combine them together and actually do some what I'll call real problems, okay? And we start off with a basic set of problems on axially loaded members. And the idea is that, well, if stress and strain are related through this constant E, if we assume everything's linear, which more often than not we'd like everything to be linear in all our designs, we know that stress is force over area. We know that deformation is change in length over original length, so we can directly relate load and deformation. And that helps out a lot when we're in design, okay? What we're then going to do is take this concept and put it through the ringer. What if we have a determinate problem or an indeterminate problem? What if we have a problem that's being subjected to thermal loads, if being heated up or cooled down? So trying to look at stuff like that and stretch that ratio out as much as we can. So that's what's coming next. So we've sort of finished, I guess, what I would call module 1 of the course. We've introduced the fundamental concept of stress, the fundamental concept of strain, and recognized they're kind of related. Well, ain't no kind of, they are. So what we'll do next is start to exercise those relationships on a series of problems. After this, we'll look at things that are twisted, and then things that are bent, and then what have you. But that's where we're going for the rest of the semester. Any questions? That's all I got. I will see you all next time. Hold on, give me 1 second.